Mathematics includes the study of quantity, structure, space, and change. Math can be so complex it could be considered strange. So strange equations could be rearranged. Don't even get me started on fractions. To multiply them is going to take a lot of action. But math can be simple. All it takes is practice. Your brain is like a muscle. Make sure it's active.
Hey guys, Mr. Ng here. Just want to let you guys know that I love math. Well, anyways, in 8.2, we're using statistical experiments. In 8.20 introduction here, we are going to have a learning target that students will be able to collect, analyze, and use theoretical and to compare experimental, whoops, that was wrong. To use data, information, to compare theoretical, zoom in here, theoretical, and experimental probabilities. So that's what you should be able to do in practice after this video. Okay, I got a warm up here. Assume that you have cards labeled with the first 15 prime numbers and you draw a card at random. So let's make sure we understand what a prime number is. A prime number is a number you can only, that number is equal to a number times 1. So for example, the first one is going to be, the first prime number is going to be what? Is going to be 2, because 2 times 1 equals that number, 2. Or I'll give you another one. How about 49 is not a prime number because that would be like 7 times 7. Those are the other factors. So go ahead and press pause. Go ahead and do questions 1 to 5 and we'll go over those together. Number 1, what are the outcomes in the sample space? The hint is write the first 15 prime numbers out. And so the first 15 prime numbers are, it's not 1. So you have 2, 3, not 4, because 4 is 2 times 2, or 4 times 1. You have 5, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, and 47. So a review with your data, this one's really good, is that the numbers are from least to greatest, and you can help yourself out by writing the numbers on top. That's super helpful sometimes. 6, 7, 8, 9, 10, 11, 12. Whoops, that says 112. 13, 14, and 15. Okay? Okay, number 2. You draw a card containing the digit 7. What are the outcomes for this event? Outcomes is which ones can I pick? So which ones have a 7 in it? There's one, there's another one, 27 and 47. And I missed one, 37. So you have 1, 2, 3, 4 of these contain the digit 7. Question number 3. What is the probability that the card you draw will contain the digit 1? Okay, remember probability is all divided by the select that you want. Okay? So here we want the probability with the digit of 1 is equal to all of them. So there are, how many numbers do we have there? 15 numbers from up here. And then which ones have the digits 1 in it? So I see, I'll just write these down, 11, 13, 17, 19, 31, and 41. So that is 1, 2, 3, 4, 5, 6 of these. So 6 out of 15, and then we can just reduce this. Three divided by 3 is 1, so your answer is 2/5. The probability that you draw one card containing the digit 1 is 2/5. Okay, what is the probability that you draw? I think I have a typo here. That you draw 21. No, it's not a typo. What? Look at this. Here's the question. Where is 21 in this list of numbers? Well, from this, remember the 15 prime numbers up there, can you select, is there a 21 in there? That would be a 0 out of 15. So that would be a 0. Remember, probabilities are numbers between 0 to 1 or 0 to 100%, because it's like, you might have something like 0.2, 0.3. You can convert it to a percent by multiplying by 100, but you can't even pick 21, so that would be a 0%. Okay, what is the probability that you draw an even number? Even number. Okay, so even is just divisible by 2. Divisible by 2 with no remainder, right? You can cut it in half evenly, as I might want to say. So let's pick a different color. So no. Odd, even. So that would still be 1 out of 15 would be your answer for that last question on the warm-up. Okay, let's go over some vocabulary words for example number 1. And the first word that we need to go over is the vocab word theoretical probability. Theoretical probability. Theoretical probability is what is expected, and I'm going to highlight that word, expected. What is expected to happen? So for example, my wife and I, when we had our first kid, we really wanted a boy first. And the total, or all of them, there's only 2 genders, so that'd be 2, and then the select, what we wanted was a boy, so there's only, between boy and girl, from the sample space, that would be 1/2. That is our expected 1/2. Each time that we have one of our 6 kids that we have. Okay, theoretical probability is what happened is what actually happened in reality. I can't spell reality. So I'll draw a sample space for each of my kids. These are my 6 kids. And then our first kid was a girl, right? And then you think the next one would be a boy. But then you're thinking next 1/2 would be a boy or girl, but I got a girl. And then the fourth one you expect, maybe like a hot streak. No, we had another girl. And then 5th child, you think, okay, you want another boy to even it? No, we had another girl. And then the 6th one was a boy. So you would think that out of all these, you would have 3 boys and 3 girls, right? You expect the probability to be 1/2, but our probability of a boy, in our case, is 2 out of 6. So our experimental probability was actually 1/3. Okay. Let's move on to the next page. Okay, let me fill out some of this, and then I'll show you guys my video simulation. If you flip a coin, so you have heads, and then you have what? Tails, they call it. My kids have been drawing dinosaurs, so tail. And you would expect heads to come up 1/2 of the time. Whoops, we did heads in light blue. And then tails would come up 1/2 of the time. And the word expect comes back in green, so let's write that in green from above. This is called what? This is called our theoretical probability. Like our TP. All right, so let's go ahead and go to the my flipping of a coin. All right, instead of me flipping a coin a bunch of times, may not be very practical, so we use something called a simulation. The computer-generated model here. And right there, number 2, in my video example, or what I'm doing right now, is I use the computer to conduct a 100 flips. So write that in the blank, 100 flips, okay? And so I press this, and I don't actually have to flip the coin a bunch of times. So you would predict that if I had 100 flips, that it should be what? 1/2 of them should be heads and 1/2 should be tails. So 1/2 times 100, your expected value is equal to the probability times the total number. So you would 1/2 times 100 is 50 tails and 50 heads. But what happened? What did I get? 50-50 doesn't always happen all the time. So here I have 45 heads as my actual and 63 as my tails. The word predict, or the expected, and then the actual is which type of probabilities. All right, so I use the computer to conduct this is called a simulation. I took my kids to a museum this summer, and you go on a simulator, and the simulator was to pretend that you're on this helicopter flying around Southern California. It wasn't real, just kind of computer generated videos right on a 3D screen, stuff like that. But I do that so I don't have to flip the coin. So in my last video there, I flipped it 100 times. And what I was talking about is in the 100 flips, well, if you want the probability of heads or an expected value, you would do the total times the probability. So 100 is our coins. N just represents the number of items you have, and P represents probability. So if you did 0.5, you multiply that in your calculator. The trick for that is, you have 2 zeros, so you're going to move it 2 decimal places, 1, 2. So you would end up with 50. So you expect 50 heads and 50 tails. And then our actual there was we had 45 heads and 63. So question, what is the actual here from our definition vocab words up here? Is that the theoretical or experimental? Well, this was my experiment. So this is my experimental probability. In theory or theoretical, that would be my TP, right? Because this is what we predicted. So, yes or no, this matched or did not match the theoretical probability. No. You can cross that off, cross that off, so no. Did not match the theoretical probability. This is called the experimental probability. In our experiment, this is actually what happened. And if you get bored, go ahead and take a coin and flip it 100 times and see what happens. And just to note, something really cool is that if you did this 100 times, 1,000 times, and let's just say that this is, ours was probably like, so this represents 45% and 63%. That doesn't really add up to 100. Maybe I stopped it early or something. Yeah, that doesn't really add up. Like, I just realized that. Let's erase that and do something that actually matches. So let's say it was this 55. Oh, it's erasing 55. Okay, so let's just say this is percent heads. And ours was 45%. So let's say 0.4, 0.6, 0.7, 0.8. Do you think we can get 90%? 45% would be something like right here. You would put a dot here. And let's just say the next time I ran it, it did 50-50. So 50% heads, I would put a dot here. And let's just say one time I did it, it was so crazy, it got 80, and 20. So 80%, there's my dot. And if you do this experiment, the simulation over, I don't know, 2 million times, you'll notice something. What you'll notice is that you'll get, it'll come all over the place, but what happens is that your dots will keep starting to stack, and you'll realize that they stack right here towards the theoretical probability, and they call this one the law of large numbers. The law of large numbers states that as a sample size increases, right, we keep testing this a billion times, the variation in data set decreases, meaning you'll go towards it. So as the sample size increases, meaning you do this a bunch of times, you'll closely resemble what the associated probability was. Okay, let's move on to the next page. Remember, we're in Module 8. This is Lesson 2, and this is Example 1 now, finding the probabilities. A student tossed a fair-sided die 200 times and recorded the results. Find the theoretical, theoretical probability of rolling an 8. Write your answer as a percentage rounded to the nearest tenth if necessary. Okay, in this example, you have an 8-sided die. And each of these, I don't know how to draw that, but it's equally likely to get a number. So, remember we have the all, and then what we want are selected. So our total is 8. There's 8 sides to the die, and we're trying to just roll one specific number. Let's try that again. The 8-sided die is from up here, and then this kind of confusing. This is the specific number we want. To roll an 8 is just, write it out. Super helpful. This is the 8-sided die, and how many of those numbers are 8? It's just 1. So our theoretical probability here is 1/8. Now it tells us to write it as a percentage. So this is a fraction. You can put this into your calculator. Calculator, I like this calculator called Graphing Calc 83. It's free. And it looks like a graphing calculator, 1 divided by 8. Okay, so there I have a decimal, 0.125. And to go to a percent is you just multiply the number by 100. So 0.125 times 100 gives me 12.5%. So this is 0.125 as a fraction. That's not a fraction. Blah. Good thing there's a right. That is a decimal. And to go from a decimal to a percent, you're going to multiply that number by 100, and we get 12.5% is our theoretical. Okay? All right, find the experimental probability of rolling an 8. Okay, now this is the actual, so let me just, this here is based off of these numbers. Okay? And do that to the nearest tenth. Okay, so we have to add all of those numbers up. So let me add up all of those numbers. 28 plus 19 plus 24 plus 22 plus 21 plus 18 plus 26 plus 42 gives me 200. Okay, so I'm just dropping my pen and throwing stuff around here. Frequency means count. So basically, the computer in the simulation, or the student tossed it and got the number 1 on their die 28 times. Does that make sense? So it's a count. So we got, our total here is, just double checking that it added up there to 200, and this is what we want. We wanted, how many times did they get an 8? Well, if you look over here, they got that 42 times. And so let's convert that to a fraction and decimal. This one's kind of nice because if you just divide it by 2, you'll get 21 over 100. And that's what percent means, out of 100. So this would be 21% is your answer. So the experimental does not match the theoretical. But if you did this a bunch more times, guess what would happen? We would go closer to 12.5%. All right, so I got 3 examples below. It says directions. In questions 1 to 3, skip one of these. When you skip one of those, go ahead and put an X through the number. That way you can have more space to work on, or it's not meant for you to do everything. But the goal is, if you need more practice, then you could do all of them. Okay, so I'm going to go over those with you. So go ahead and press pause, do the 2 questions that you want to do, and then press play when you need some hints, or if you want to do that with me step by step. All right, number 1, a student spun a spinner with 4 equal sections. So let's just draw it, super helpful. 100 times and recorded the result. So you have red, blue, green, and yellow. Find the theoretical probability of spinning a blue. So probability, this would be better, probability of blue is equal to the total versus the select, what we want. So total is how many colors? There are 4 colors, and select is blue. And okay, pay attention here. Blue is not the frequency here, okay? Remember this, this here is matching the experimental, so don't do that. In this case, you're just looking at the spinner over here on this circle here. So 1/4, remember you don't need to calculate, you can just type in your calculator. Remember, if I just get this to out of 100, there's my fraction, and 4 parts out of 100%, right? Like 4 pennies out of 100 is 4 cents. 4% is your answer, is the theoretical. All right, let's find the experimental now. Same thing, we want blue. And in this case, the experimental is we had 100 times. And blue came up 38 times. So that would give us a decimal, and then you multiply by 100, and you would get 38% is your answer. Okay, so through a fraction it is easier, and it says rounded to the nearest tenth. Let's do a quick fraction lesson. That would be the tenths would be this spot right here. This spot is the hundredths, and so that helps you round up or round down to get to the tenths, okay? All right, let's try question number 2 here. A student flipped a coin 125 times and recorded the results. Find the theoretical probability. So let's go and do the theoretical probability. Again, this is the total, or another way of saying is the all versus what you want, the select. Well, if there's only 2 choices, it's either going to be heads or tails, so it's only 2 of them. But we're trying to get heads, and so like you can just write this out, right? You did the coins before. There's 2 coins, so that's the total, and you're trying to select a head, so that would be 1/2. And again, you can just put that into a decimal in your calculator. That would give you 0.5, and then if you multiply that number by 100, this gives you a decimal, I'm sorry, a percent. So 50% is my answer. Okay, so review, 1/2 is my fraction, 0.5 is my decimal, and then 50% is my percent. Okay, so remember, the chart here refers to the experimental probability. So now we need to find what happens actually in our experiment. So the total, how many times did I flip this coin? 125 times. And what did we want, or what did we select? We selected heads, which is here, 73. I'm just going to change that into a, let's show you the calculator one more time. 73 divided by 125, enter. You get 0.584, and if you multiply with that number times 100, you get 58.4. So 0.584, and then we multiply this by 100, then you will get 58.4%. So in theory, we should get only 50% heads, but ours was 58, so ours was a little bit higher. All right, let's go ahead and try question number 3. All right, let's go over question number 3. A fair 6-sided die is rolled 150 times. Find the theoretical probability of rolling a 3. So the theoretical probability is all of your probabilities over some of them. That's another way of saying it. So we have 6 die, and there's just one number. Again, list out all the numbers, that might help you. 1, 2, 3, 4, 5, 6. And we're trying to roll a 3, so that's only one number, so 1 out of 6. If we put that into your calculators, you'll get a repeating decimal, 1.6666, right? And so how do you round to the nearest? Well, first of all, we're going to multiply by 100. Now that would give me 16 point. And so my decimal would now be here. This is the tenths. And so I'm going to actually look at the hundredths. And this number is 5, 6, 7, 8, or 9. You're going to round this number up. So that would be a 7. 16.7% is our theoretical probability. The experimental probability, we're going to look at this chart here. So we have the all, in this case that would be the 150. Rolling a 3 is, this came up 27 times. And so if I put that into my calculator, let's do that. 27 divided by 150 gives me 0.18 is my decimal. Okay, common mistake, 0.18 is not a percent. If you did put the symbol percent, that would be less than 1%. So multiply that by 100 to get your percent. Our percent is experimental. That was pretty close, right? 18% matched close to the 16.7%. Okay, let's try this one. And here we're talking about, now we're on Module 8, Lesson 2, Example 2, Design and Run a Simulation, and 8.23, Run and Evaluate the Simulation. So what is a probability model? Probability model is a mathematical representation of a random event. What's the probability it's going to rain today? What is the likelihood of catching COVID when you go outside with no mask, right? That's like a probability model, something that happens. And it consists of the sample space and the probability of each outcome. Okay? So what's the probability model that you get in, the likelihood that you get into a really good university, like say UCI? Okay, what's a simulation? Simulation is a probability model to imitate the process or situation. Coins, we've done that before, dice, and random number generators, like basically the computer calculator can generate numbers at random, can be used to conduct simulations of experiments that might be difficult or impractical to perform in reality. Would you really want to flip a coin 10,000 times or roll the die 100 times? Okay? All right, so let's talk about steps to conduct a simulation. The first thing you need to do is determine the probability model. Okay. Number 2, define the trial for the situation and state the number of trials to be conducted. Number 3, we need to conduct, or actually do. And then number 4, we have to analyze the results. Okay? All right, let's try this one. Let's try this example over here. A company that produces bottles of water runs a promotion in which 1 out of every 8 bottle caps wins the customer a free bottle of water. Okay, and so basically what we're going to do is we're going to determine the probability model here. So the question you might want to think about is, what are the outcomes? So you open the cap and you either win or lose. So there's 2 outcomes, 2 totals, right? And here you also want to calculate the theoretical probability. And that would be to win, it's only 1 out of 8, so 1/8. So winning theoretical probability, and to lose theoretical probability would then be what? 7 out of 8. Because 1 plus 7 is 8, and that would be 100%. So 1 time out of 8 you will win, and 7 times out of 8 you will lose. Okay. Let's go ahead now and define the trial for this situation and state the number of trials to be conducted. So what can we use here? There are 6 available probability tools: cards, tossing a single coin, marbles, standard die, random number generator, and a spinner. Can I not count? 6, sorry. All right, which of these tools can actually give us something like this? You could use, take 8 cards. Let's highlight it. Cards would work. Okay, a coin toss is 50-50. You can't just say win or lose and just keep flipping it, because that'd be only 2 outcomes. But we have a total of 8 because it's 1 out of 8, right? So you can't use the top coin toss. Marbles you can, right? Let's just say you have 8 marbles, and of those marbles, 7 are red and 1 is green. Green means you win, red means you lose. Put it in a bag and you draw it. So marbles can work. A standard die, standard would just be numbers 1 to 6. So that one would not work. A random number generator, yeah. If I put the numbers 1 through 8 on it, and then I choose number 3 to win, and then all the other numbers are lose, and then the computer picks one, so that would work. And then I can choose a spinner, because if I had a spinner and there's 8 spaces, again, I could put 1 green, 7 lose. So let's just write that. You could pick any one of these. I think the easiest one to pick would probably be something like cards. Have 8 cards. Write win on 1 card. Right. Try again. On 7 cards. Pick one at random. Pick one at random. And I kind of told you what my thinking out loud is for the other ones. Okay, that's to define the trials. State the number of trials to be conducted. The nice number to run is kind of like 100. We will run simulation, or we will run this experiment 100 times. So turn the cards over, pick one, record the results, flip it back over, and do that 99 more times. Okay? Okay, so to conduct the simulation, you actually just you would do that. You would just conduct it. Do it. And then you would analyze the results. Record it. Here's a sentence might help you. In one simulation, or the winner was recorded 12 times in 100 trials or experiments. So that would effectively give you a experimental probability of 12% when the theoretical probability of 1/8 is about 12.5%. So pretty close, pretty close. Okay, let's cover the directions here. In questions 4 to 5, skip one below. So either you're going to choose Tiana or Lamar and try it yourself and then press play to check your answer, or if you want to do the problems with me step by step, then just let the video continue. Number 4, internet. So Tiana sells handmade earrings online. Last month, she sold 60% of her inventory. Design and run a simulation that can be used to estimate the probability of selling inventory. Okay, so we can just list our outcomes. She sells something 60% of the time, and then no sell 40% of the time, right? What else do we got? Our theoretical probability is already 60%. And then experimental probability, that means a no sell would be at 40%. So we already kind of did that above. What else do we got to do? Okay, what would you guys use? You can use any of those. I don't know. Let's pick marbles. Let's just say marbles. Take 100 marbles. And I really like the colors green and red. Green means go, red means stop, right? So 60 green marbles represents, she makes a sale. Sale. 40 red represent no sale. Stuck in her inventory. Does that make sense? So we can perform, you can just however many times you want, perform 50 trials and record data. Does that make sense? You put 100 marbles in a bag, 60 of them are green and 40 are red. You pull out a marble and you tell us what happened. You record the data. On my first trial, it picked out red. Second trial, green. Then third trial, green. And you keep doing that. And let's just say then you have your results, right? So going through this, we determined the probability model. We defined the trial for the situation, state the number of trials. We said 50. We conduct it, and then you analyze it. So let's just say you did this. And based on the simulation, and what's cool is if you just go to Google and type in like coin simulation, die simulation, marble simulation, you can find things that will actually just help you do that. Based on the simulation of selling inventory, maybe you get something like 64 greens. And not selling, you got 36 reds. Well, we did 50, so 50 times, try that again. So let's just say you, 0.64. So you have 50 trials and you pick 32 green, because 32 over 50 gives you 0.64, and then you pick 18 marbles that were red, and that's how you get your, if you had to analyze it. Okay? Okay, let's try number 5, programming. Lamar designed a soccer computer game. He coded the program such that a player will make a goal on 35% of the attempts. Paula is testing the game and thinks there may be an error in the game's programming. She attempted to make 30 goals and only 4 were successful. Run and evaluate a simulation to decide whether Paula is correct. All right. So let's take a look at our outcomes. Our theoretical probability is 35%. 35, make it simple. I call it yes or no. So yes, make a goal. And then these are complementary. Basically means 35 plus something equals 100%. So 65% no, you're not going to make a goal. This is the theoretical probability. The outcomes are yes, you're going to make a goal, or no, you're not. Okay, so what kind of systems can I use here? What kind of way to model the simulation? What you can use is we can use something called the random digit generator. Let me just write it out. Random digit generator. RDG. Don't use abbreviations, you should write it out. And basically, numbers 1 to 35 will be, so we're assigning these numbers. So if you get the number 1 to 35, it's a goal. Numbers 36 to, actually it should be 0 to 34. And we can just do 36 to 100 is a missed goal. Missed goal. Okay. And we're going to perform this. You can pick. Doesn't matter how many times, but you know, Paula tried it 30 times. Does that make sense? That was her how many trials that she did. Trials. But it's always, you don't have to, but of course more trials the better. So perform, I always like the number 100, perform 100 trials and record data. Okay, so let's try this. I'm actually going to take you to the graphing calculator. And I'm going to go math, probability, random integer. And what's nice about this is it's actually telling me the code. It says random integer, parentheses lower, so that's the lowest number, 1, comma to 100, and then the number of trials we want. So it's just telling me to pick numbers. Does that make sense? And let's just say I know we're going to do it 100 times, but let's say I pick it once. I got a random number, and the random number is 85. So what does that mean? We said, well, numbers 36 to 100 represent a missed goal. So you can just keep pressing enter, and it repeats the same. So this one would represent, again, a missed goal because it's between 36 and 100. Missed goal, missed goal, missed goal. Keep pressing it. Oh, there's a goal, right? So let's just say we do that and calculate our data. So let's just say I do that and I calculate based on the simulation, the experimental EP, probability of making a goal. Let's just say I do that 100 times, right? I press enter 100 times, and 41 times it comes up between a number 1 to 35. Making goal is 41%. So 41, that's a 1. Blah. 41 of 100. And let's compare that now to Paula's. Paula had a success rate, where she scores a goal, success rate of only 13%. That is 4 out of 30. So Paula could say your game's rigged. I only got 13%, and you're getting it at 41%, and you're telling them it's supposed to be 35%. But the law of large numbers says if you keep doing the simulation, we're going to go towards the 35% that Lamar kind of designed it to be. Okay? And if you want to do 8.24 extra examples, these mixed exercises, record it, and then you can send it over to me, ing_d@auhsd.us. Okay, so that is lesson 8.2, statistical experiments, and we're able to collect, analyze data, and compare the theoretical to experimental. We'll see you guys later. Bye.